Primary design goal. Our primary design goal was that we wanted our bridge to be a truss bridge. We believed that triangular units would create a strong bridge that would be able to hold a heavy load. We also wanted to be cost efficient when building the bridge, making sure not to use an excess amount of materials. We had no specific goal that we were trying to optimize, but we were going for an all-around bridge that would achieve the reach goals in cost, weight, and performance.
We designed our blueprint of the bridge using AutoCAD. The bottom drawing is of the view from underneath the bridge, the middle drawing is of the side view, and the top is the top view. Our dimensions for the whole bridge were to be 2 feet long and 6 inches tall. The width was 4 inches and the top piece was 1 foot long. The final bridge ended up being pretty close to what we planned with our blueprint. The length, width, and height all aligned according to plan. The only big differences were with our trusses. We didn't include as many trusses at the ends of our bridge like we planned to, and we had to make room on the bottom of the bridge for the testing device. We did this by moving the middle support over 1/2 inch and adding another support a 1/2 inch from the center the other way, leaving a 1 inch gap for it to fit. For the mid-semester testing, our bridge passed with ease. The test was simple. All we did was put the bridge between 2 boxes and hung a 1 kilogram weight from the bridge. The bridge didn't break and passed the test. We didn't notice any major improvements that we had to make on the bridge, but we did end up adding a truss for each corner of the bridge.
Our original blueprint had diagonals in the smaller trusses of the bridge, but we cut those out in order to save time. After testing the prototype, we decided to add these diagonals to only one of the 3 small trusses, once again in order to save time.
In the final test, the bridge was loaded in 1 kilogram increments up to 5 kilograms. An Arduino with an ultrasonic sensor was used to measure deflection of the bridge, and force sensors were used on all 4 corners to measure force in each corner. The bridge had an overall satisfactory performance. It was able to hold 208 times its own weight. The bridge had a total deflection of 8.61 millimeters, plus or minus about 0.17 millimeters. Overall displacement was calculated with 15 values collected over 3 seconds from the Arduino. The ultrasonic sensor has an error of 0.17 millimeters. This was calculated by the variance shown over 15 values collected with no load on the bridge. The displacement was overall linear, increasing as the load was increased on the bridge.
For the pressure sensor data, the leftmost column shows the time at which the data was recorded. The next 4 columns show the reading of each sensor. The final column shows the total weight readings of all 4 columns. So this data tells us that our bridge weighed about 0.369 pounds, and our bridge with all the weights on it weighed about 11.4353 pounds.
Cost. The overall cost was 142 Martian dollars. With the money, we bought tool communal access, 20 Martian dollars, wood glue, 10 Martian dollars, 1 plate of wood, 50 Martian dollars, 6 sticks, 30 Martian dollars, 1 piece of sandpaper, 10 Martian dollars, 24-inch masking tape, 2 Martian dollars, and poster paper, 20 Martian dollars. In the beginning, we bought lots of materials, but in the end, we had an excess amount, so we sold the leftovers. Future improvements. There are many future improvements that we would have made if we had the chance. Some improvements we would have made were to add more diagonal trusses for support, add more trusses on the bottom for better diffusion of weight, strengthen joints with gusset plates, restructure bridge so all joints fit together perfectly, and we would make more accurate measurements for all the pieces.
The stretch goal that we worked towards was the light notification system on the Arduino. We created a system that evaluates deflection from under the bridge. As deflection increases, the lights go from green to yellow to red. In our lab testing, we had the sensor above the bridge. To account for this change, the code can be revised to change the lights as deflection increases instead of decreases.
This following video is an example of the stretch goal that we accomplished. Now, here are 2 videos of our group testing the prototype bridge.
Never. All right, put her on.
Clearing.
You ready? Yeah. We're good?
Yeah.
Wow.
Yay!
Are you going inside or outside?
Inside.
Wait, I want to.
Outside.
Outside.
Yeah, so that one.
Okay.
Oh gosh.
Where's the...
where's the other one? Just put it in like the middle sometime.
In conclusion, our bridge held more than double the amount of required weight, cost less than half of the budget, and deflected only 8.61 millimeters. Our final bridge was almost identical to our prototype bridge, meaning that if we had extra time to work on the bridge, more weight could have been held.